This is a recap of where we got to on this very extended and very significant memo about position and velocity graphs. This is the situation we had for the second problem. And we had a graph where the position, this was y, I didn't want it to use x because it's confusing, y of t was equal to t squared. And let me put that in the little notes here. Okay, so position y of t was equal to t squared. And what we want is, we want to understand the instantaneous velocity at any time t. It's a very ambitious thing. I'm intentionally kind of skipping ahead a little bit so we can get some really powerful tools. We have only started to understand how to get the instantaneous velocity at a single time t. And already now I'm asking, well, we could do this for any time t, and I think it'll be very useful for us. And it'll give us good practice in finding the instantaneous velocity at a particular time. And it'll give us a clue as to some massive shortcuts as well. So we want to understand the instantaneous velocity at any time. And the big observation that we talked about a bit in class is that that allows us to graph the velocity as a function of time. And we've toyed with that idea a little bit. And so I asked you to just sketch what you thought the velocity looked like. So let's think about what this motion looks like. It's something, let's think y as height, for example. This is something that's coming down, bouncing, and then going back up, basically. Coming down to a minimum at 0, and then going back up. So there's downward motion, then there's a moment when it's turning around, which is going to be very interesting to us, and then going back up. Okay, so let me put that in our little notes. So a verbal description of this is going down, turning around, and then going back up. And that's exactly what this velocity graph indicates. All down here, we've got negative values for the velocity. Up here, we've got positive values for velocity. When it turns around, momentarily, it's stationary. We get 0 for the velocity. That's a very significant fact. So this, I put a question mark here because this was a lot of people's guess as to what the vague shape of the velocity graph was. People had different variants on this kind of thing, but everybody, I think, got to a point where it was a big negative number corresponding to a big negative slope here. Let me draw another tangent line here. Okay. Notice what am I doing here? That's a secant line. But if I make these really close together, it stops changing very much, and it looks like a tangent line. Okay. So there's a tangent line with a large negative slope. And if I then scoot it down so that it's looking here, it's not as negative a slope. And down here, another tangent line, even not as negative a slope. So those slopes are going from large negative numbers like -5, -4, -3, -2. And so it does look like this behavior of going from very negative, moderately negative to 0. And then over here, let's maybe use this guy. Over here, we've got tangent lines that are a moderate slope, and then as we go over here, a bigger slope. And so these are recording what's going on. And the way they're recording it, as I want to emphasize this again, is that the v of t graph, the height of the v of t graph at time t equals the slope, because that's what velocity is for a position and time graph. It's slope equals the slope of the y of t graph at the same time. And we're not sure if this is exactly what, this probably isn't exactly right. It was just a freehand guess. But it's got the right qualitative behavior. Very negative, moderately negative, 0. Moderately positive, very positive. Now, the question is, how do we make that more precise? So we want to focus in on, let's say focus in on just t equals 2, say. And I'm just going to freehand that. And then what we're going to do, remember the tangent line, it's very important that we couldn't just say, oh, it's just going to pick any other point, 0 to 2, and find that slope. That worked for a straight line. It worked for number 1. It will not work for here, because these guys all have different slopes. And this one incorporates a heck of a lot of information between 0 and 2 that's not interesting to us. That's the average or overall velocity from 0 to time 2. What we want is something that concentrates very, very close to t equals 2. So we want to take something that's very, very, very close and find the slope of this line. And what we actually found, there's a strategy on page 91 with those problems, and also with the previous memo, is that we might take t equals 1 to t equals 2, and then 1.9 to 2, and then 1.99 to 2, and 1.999 to 2, and see if there's a trend towards a simple number, and kind of hope optimistically that it will be. So, for example, that's how you would try to calculate. We want to fill in this table of all these v values. If we want to fill in this one with the question marks, what are we going to do? We're going to use things like a pair, t equals 1.9, t equals 2, and then maybe t equals 1.99, t equals 2, and then t equals 1.999, t equals 2. Have 3 different people do that, maybe, and then see, is there a trend in these numbers? Okay, so what I mean each time here is go ahead and use those to calculate a secant slope. Use these to calculate a secant slope. Use these to calculate a secant slope. None of those will be exactly the tangent slope, but if it looks like they're getting closer and closer to some fixed number, then that should be the tangent slope. And it turns out, for nice functions, we get nice answers, and we'll be able to guess these answers, and it will turn out to be a very, very interesting place to be once we start to get those answers. And that's about where we finished up. I wanted to make sure I kind of wrap that up to make it clearer about where we are. We're not finished. We've got a lot to do. Don't worry if it's still a little hazy, but we're in a good place.